Thank you. Hi, everyone. So when I was invited to give this talk, the actual results were fresh out of the press. There was a lot of news, a lot to read, a lot to digest. Now it's been a few months. My excitement has gone down. I'm still excited, but it was a lot of work and it led to amazing things, but there is also more to come. And so I readjusted a little bit the slides to tell you about the actual results, but also to give you some perspective of what do we do next, just to keep us moving. So I'll talk about Science Observatory as well towards the end of my talk. Oh no, I need to use this one. Move it was working. We tried it, and now should I try again? No, changed his mind. And if I advance slides here, I can't, right? Oh, it moved, but I don't know why. Let me try one thing. Yeah, I can do it with the laptop, so I don't need this. Okay. Okay, but this, oh, now it works. Okay, fine. Okay, so I don't need to give too much of an introduction to the topic. I am sure everyone in this room is familiar with the CMB. The speakers before me have covered multiple aspects. The only reminder I want to make, and the reason for this is because I'm going to be talking about that and showing some stuff around that, is that what we're talking about here is looking at the universe, the early universe with the CMB, which means mapping the properties of the CMB radiation in temperature, polarization, and then with gravitational lensing. And from these maps, we then, write down all the physics and all the phenomena that are happening throughout the universe and map that physics into the features of the angular power spectra. Angular power spectra then span, as I said, the temperature and polarization and lensing, and they all show different features and different signatures of the components and the physical processes of the universe, and those are the things that we're going to be probing with the CMB. Right, so we have been doing this for a number of decades now. This is a summary figure of where the field is in terms of measuring this power spectra as of March of this year. There is a collection of different observations from different experimental campaigns. We have had satellites, balloon experiments, and then ground-based experiments that have been mapping the CMB. I'll mostly be talking about the small scales, which means that for me, Planck, it's just an addition today for this talk, and it's covering and probing the large-scale behavior of the universe, and then the main observations that we will be looking at are the arc-minute resolution, finer resolution scales that are probed by ground-based experiments. And this has been done over the years as well. So there has been a combination of space and ground-based projects working together to map this power spectra across all scales. And we're going to continue to do so. So this is a jump into the future of how these power spectra project into observation in a 10-year time scale. And what you see here is that there is the same kind of principle where you are going to have more satellite observations from the proposed Lightbird mission combined with what is an ongoing experiment at the Science Observatories that gives you the intermediate to small angular scales. Okay, so I'll be telling you about, as of today, this was March 25, but as of today, from the Atacama Cosmology Telescope, and then briefly touch on the Science Observatory. Right, so the Atacama Cosmology Telescope, from its name, we guess that is a cosmological telescope located in the Atacama Desert in Chile. It's a 6-meter I'll be talking in the past. It was a 6-meter telescope that observed the sky from 2007 and 2022 on a plateau that is really ideal for cosmological observations because it has got low water vapor, so very dry atmosphere, which is really important because the CMB is usually contaminated by atmospheric emission. But also because it's located near the equator, we get a really good sky coverage. We get to observe a lot of the sky that spans over the telescope. I say a was because it's gone. So this is this is a picture of the outside, basically, of the telescope leaving the site. So ACT has been decommissioned, dismantled, and the platform is now hosting one of the Simons Observatory telescopes. Say that go. I think, and there are some other ACT people in the room, I think this was donated to a science museum, or that was the intention. But I mean, one of the things that we need to consider when we build these telescopes and projects in the world, in very remote places, that you need to take them away at the end of it. You're also responsible for dismantling and clearing the site once that they've done. Yes, so the collaboration that has worked on, well, getting the telescopes, building it, and then collecting the data and analyzing the data over the years has been a pretty small collaboration when we think about the large, huge projects that we work in today. We were about, well, ranging between 50 and 100 people over the years, led by Princeton, and the telescope and the main instrumentation support came from the NSF. The instrument has had 3 different phases over the years. When it started observing in 2007, it was a telescope measuring only the temperature of the CMB, so just mapping the sky in temperature. And then this is one of the advantages of having an instrument and a telescope on the ground. We could upgrade it over the years and move from temperature to temperature and polarization. So in its final configuration, we had 3 different detector arrays that were collecting images of the sky at 2 different frequencies, each of them at 2 different frequencies at the same time. And this has been one of the biggest advancement in terms of the technology for CMB detectors, the ability of having a single detector looking at 2 frequencies at the same sky has allowed us to expand in a way the focal plane without needing too much space. At the end of the observational campaign, we have covered about 45% of the sky. And these specific, so the yellow footprint here is the layout that was covered by the final survey. And the specific footprint was chosen in a way to have both areas that are deep in terms of, like observations focused over the years to reduce the noise, to have very deep measurements, but also at the same time large sky coverage, because some science goals really benefit from as much sky as possible, but also in this way we were able to overlap with many other surveys of the sky to allow us to do cross correlations as well as other combined studies. So what we put out in March is what we call the data release 6, and this is just a cumulative number representing all the different data releases that have come out of the collaboration. The data that were part of this release include observation collected during 2017 to 2022, mostly using solely nighttime observation. And I think the most interesting figure to look at are these intensity and polarization noise levels that show two things: how the data of ACT itself have improved over the year, going from data release 4 to data release 5 and 6. But then I guess the striking point for people who use the CMB observations, so maybe they don't work on them, but they are familiar with their sensitivity and importance for cosmology, is the comparison with what Planck has achieved over here and here in temperature and polarization, and how ACT has gone a lot better than Planck over a very large sky area. So this is the new state of the art in terms of CMB observations. So the presentation of the sky maps and the cosmological results were released in March in a set of 3 publications, and I will be presenting results from these papers today. This is a zoom in. Well, we found out when we were trying to prepare the data release and also like how to present our results, we found out that it's pretty difficult to have, we don't have the pretty images that Euclid or other surveys can get of a nebula or a galaxy. So we need to explain blobs to our colleagues and also like to the wider community. And some of our colleagues made this amazing video because we can't also show all of the map on a single 2D plane, and so that we have this rotating sphere that moves across the observations, and I have a little cut of that video later on. But this is a screenshot of one part of the sky with a zoom-in region, and this is a combination of Planck and ACT observation, just highlighting the high resolution that you obtain when you add Planck. For example, this is the Sculptor galaxy that comes out very visible in our observations. And then the same for polarization. This is the first time that we have a high signal-to-noise measurement of CMB polarization. Planck was not designed, that did not achieve that. He provided some polarization data, but nowhere near the level of sensitivity that we have today. And then for people who are interested in the astrophysics more than cosmology, this is an example of how then putting together multi-frequency observations, you can pull out some areas of the sky very well mapped also for other sorts of studies. Okay, so when we show you a CMB map, what you're looking at is either the CMB at a given frequency or a combined CMB map pulling together all the different frequency. What we really have, as I mentioned earlier, are detector arrays that are sensitive at different frequencies. And so our main data set is a collection of CMB power spectra at different frequencies. I will not go into the details of these, but just to give you a sense that what we work with is a number of objects, and we need to model them all to be able to then extract their combined sensitivity and cosmological power. The point I want to make here is that when we do this modeling, cosmology and the physics of the universe is only one component of it. A lot of stuff that fall into our observations is not primordial, is not the physics of the primordial universe, but there is a lot of astrophysics of sources, both galactic and extragalactic, which we need to model. And this is something that the community has got used to. We have been doing it for ACT, for Planck, for other projects, but there is a huge amount of uncertainty on this modeling. And when we work with it, we set as a goal to be able to model these astrophysical foregrounds so that they don't bias the cosmological results. But we don't really care about the exact astrophysical answer on those foregrounds. So it's more of a way of saying, okay, I'll build an envelope for what is not primordial. And then as long as that envelope does not bias my cosmology, then I'm fine with it. And then you can remove what is non-cosmological and get to the pure CMB power spectra. At the top, there is temperature, and then the E mode of polarization and the cross correlation between temperature and E modes. in terms of the TE spectrum. What you see here is the overlay of the final observations from Planck in orange, and then the new ACT observations in blue. You also see that it's becoming really, really difficult to appreciate the measurements on these plots. We already had to go to L times the L to be able to show off better the measurements. You can't appreciate the error bars. The data are so precise and cover such a huge range of power and scales that it's really difficult to appreciate them in the usual way, or how we were used to do. You see that the ACT data extend the Planck measurements to smaller angular scales. It was designed to do so, but it's still nice to see that this is happening in such a great way. There is also very good consistency between ACT and Planck on the scales where they have common measurements. And then in terms of polarization itself, ACT is really dominating the measurements at all scales available to it. Okay, so once we collected the maps, processed the observation, and derived our baseline data set, then we went and studied the models that were best fitting our observations. There is a theory here that is plotted in gray over the observations, and that's the best fitting model for them. But before going into the details of what is the cosmological answer, we wanted to be able to explain to the community of how we were going to be providing constraining power on new physics. And so what you see here are model differences for the three power spectra that I mentioned earlier for three select non-standard cosmological models. So in blue, we are showing what extra free-streaming dark radiation would look like compared to lambda CDM. In gold, it's what a contribution to dark matter from axion-like particles would look like. And then in red, a non-standard recombination history. With the details described by those parameters over there. And so you see that all these models have features and differences compared to the standard lambda CDM model. Now, if you plot on that, what Planck can do for those models, you get these bands. So here, the edges of this band, these black lines, are showing the Planck sensitivity to those cosmological models at those scales. And you can see that you can't really tell apart these different models. When you add ACT, you start to really be able to distinguish between them. And this is happening at very small scales in temperature and in polarization, so above L of 1,000 in TE, for example, but then it's at all scale in polarization in EE. So really, that's a completely new channel that is available for discriminating between different cosmological models. Okay, so we kind of went in order, right? And the first thing that we that we derived and we tested was lambda CDM, which was the standard cosmological model that was consistent with observation when we were looking at our data. What we found is that the lambda CDM parameters coming out of ACT were really consistent with those derived by Planck. That this model was a really good fit to both set of observations and across all channels that were available to us. We found that the combined, so that in some parameter space there is really complementary and orthogonal information coming from ACT and Planck. And so then when you put together the two data sets in what we call the p-ACT combination, you improve on the limits that you have from Planck alone. And so this again becomes a new, more stringent constraint on cosmological models. We tested parameters from different channels and found really good consistency across the results. And then we looked at parameters that can really stress test the assumptions of lambda CDM. So, and again, I don't need to give too much introduction about this for this audience, but you know that, that there have been some analysis of Planck data that were showing excess lensing or evidence for curvature, and we don't see any of that in the ACT data and in the p-ACT combination that comes out of it. And then the other key parameter that obviously had a lot of interest was the Hubble constant. And what we get independently of Planck on that measurement is consistent with the Planck results. And therefore, we see with the ACT observation the same tension with the shoes measurement that is present in other CMB estimates. We wanted to check, well, once we established that lambda CDM was a good fit to our data, and we got our baseline lambda CDM solution, then we wanted to check how this compared with observation at lower redshifts. And for that, what we did was simply to predict what those observations should look like and compare with the leading observations. So we did that for CMB lensing, for BIO. So at the time we were producing these results, only DAISY DR1 was available. But we have redone this with DAISY DR2, and it's basically the same. And then with the supernova, we used the Pantheon combination, and we found really good agreement. Our lambda CDM solution was able to predict these observations really well. So since we are in good agreement with that, then we can also combine and use the combined data set to break degeneracies in cosmological models. This is an example on some key parameter in the lambda CDM model, where on top of p-ACT, we now have LB that stands for lensing and BIO. And you see that the contours continue to shrink and provide tighter measurements. Okay, beyond lambda CDM, so of course there was a lot of, there is a lot of discussion within the community about the things we don't know about lambda CDM and trying to understand if we don't know them because, maybe the model is not correct. And so we drafted a list of cosmological models that were either well motivated from a fundamental physics point of view, from a particle physics, astroparticle point of view, or that had been proposed specifically to address some of the issues in lambda CDM, for example, to reduce the Hubble tension and to explore the dark sector. We ran all these models through the observation in the exact same way we did for lambda CDM, and we find no statistical significant departure from lambda CDM. For some cases, you find a 2 sigma deviation, but that is not strong enough. There is not a statistically enough preference to be able to say that those models were actually better than lambda CDM, especially when you account for all the extra parameters that those models bring in. We then, by doing that, we obviously set constraints on the parameters of this model. This is just like a selection of some standard single parameter extensions to lambda CDM that are looked at in cosmological analysis. And we found good consistency for all of this model with standard model predictions. And by standard model predictions, I don't mean just cosmology, so not just lambda CDM, but also from Big Bang nucleosynthesis or particle physics, all sorts of standard model predictions. And then we found, and I'll come back to this later, that the models that had been constructed specifically with the aim of increasing the value of the Hubble constant that we extract from the CMB were not preferred or favored by our data. We also tried to describe specifically for each model what was the CMB contribution to that model. There is one of our colleagues in particular who always asks, okay, fine, there is a new paper, but what is your data bringing to the table, right? So we wanted to make sure that we were highlighting what ACT data was telling us. And an example of this is the new constraints on W0 WA when you fold in DAISY BIO and supernovae. The leading driver of that result is not the CMB, right? You can swap CMB dataset, you can use any combination of CMB experiments and you get the same answer. The driver there is in the BIO and supernova datasets that you pick. So we emphasize that, and we also noticed that for some models, so for example, when you try to constrain the number of neutrinos particles in the universe, so relativistic species, you pretty much get all the way there with the CMB alone. You can add a lot of external data sets and the number moves very little and sensitivity improves very little. So the CMB is really, really powerful in giving you that answer on its own. Okay, so now I will only give you a couple of examples of extended models that we constrained, and then I'll move on to SO. So this is new constraints derived exactly on the effective number of relativistic species. And this is the standard model prediction of 3.044 that you get by calculating exactly what you expect with 3 neutrinos and then all the different corrections that you need to add to that. And this is the new results, the new distribution that you obtain with the ACT observations. For each model, we try to interpret the results, not just putting out the number. So, right, yes, an effective is 2.89.011, but what does that mean in terms of physics? So we try to extrapolate that down to a physical interpretation of that results. And for example, we can interpret that measurement in terms of how much can we rule out contribution to radiation coming, for example, from a spin 3½ fermion. And you can rule that out by looking at the probability distribution of excess, of a specific excess in this distribution. And then this measurement also translates on bands in terms of variation in an effective caused by different energy injection, if you want, into the universe from different particles. We found no evidence for non-zero neutrino masses. So the results on the neutrino mass that you get from adding ACT observation is not that different from what you get from other CMB datasets. But this is one of those parameters that it's really dependent on some other cosmological assumptions that you made. And there is a correlation between the value that you get for neutrino masses from Planck and the XX lensing that is present in the Planck observation. So for us, it was important to test that this was not happening. Again, we stress the fact that the results that you derive on these parameters really depend a lot on the BIO dataset that you're using, which is really crucial here to break degeneracies, and I'll comment on that later. I want to mention this briefly. So there has been a lot of work going on this early dark energy model in the community, both from a theory point of view and then from a phenomenology and data analysis point of view. This model got a lot of traction because it was one way of increasing the Hubble constant. And there was a hint in the previous ACT analysis at the level roughly of 3 sigma that this model could be preferred over lambda CDM. So for us, it was really important to first check if this was still there and then B, understand how strong that was. And that went. So with the new ACT DR6 observation, we do not find any preference for early dark energy. And we were able to track this down to the data itself, where that was happening. And there was a specific feature in the E mode of polarization at intermediate scales between 700 and 1000, where there was a feature in DR4 which was massively reduced with new statistical power in DR6. So this was one example where having more statistical power in your observation can completely cancel a statistical fluctuation that was there before. Okay, and then I'll just jump to a couple of comments I want to make. So I said that we tested a bunch of models that were specifically built or interesting because they were going to move the H0 value from the CMB towards higher values. I guess, okay, this is a higher level summary of what we find. We grouped each class of models that we explored, like if it was touching the physics of primordial perturbations or pre and modified recombination physics or particle astrophysics or late time physics like dark energy or modified gravity. And what we saw is that the ranges of H0 values that we got by exploring all of these models were really confined in these boxes. So these boxes are telling you the lowest and highest value in H0 that you can get by varying that physics. And these boxes cannot get you to the shoes values. So that, you know, if you did this for Planck or for previous ACT results, these boxes were much broader. And so those models were potential solutions or would have allowed you to get closer to the gray band, but that's no longer the case for ACT. And you know, all the 2D correlation in parameter space that allow you again to move in that direction are also cut out with this new analysis. One thing I want to comment on, I mentioned already a little bit earlier about the dark energy equation of state. This is my take probably on what's happening right now. I think what we are seeing both in W0 WA and in neutrino mass in terms of this very tight measurement of the neutrino mass, meaning that, you know, if you allow it to go negative, it will go negative. It's simply mapping these measurements of omega matter into a different parameter space. Because, you know, there is the measurement from the CMB and the measurement from DAISY or from supernova, according to how you put together these different posteriors, you can get evidence for other physics effect in different parameter spaces. Okay, so the data are publicly available on Lambda and on NERSC, accompanied with all of the data products, all of the analysis outputs in terms of MCMC chains, power spectra. There is a list of notebooks that allow you to go through the observations and the analysis to reproduce it and then, you know, make your own and build on that. And I encourage everyone to look at it and to use these observations. Okay, so just moving on a little bit into the future. So if you're working with the CMB observations right now, if you need to plug in anything into one of your cosmological analysis, what you will be using for the next year or two are going to be the latest observation from ACT and the latest observation from the South Pole Telescope, which recently released the new data set from their main field, and there will be more to come from them as well. So, when you're going to do CMB plus something, cross correlation, galaxy shear, galaxy clustering, or whatever, probably these are going to be your two main data sets for the coming year. Then after that, I want to mention the main project that is happening from the Atacama Desert. So the Simons Observatory is, well, we used to say the next ground-based project, but it's really the new current ground-based project that is taking place in the Atacama. It's an array of 7 telescopes which will host a little over 123,000 detectors when they're all fully operative, observing in 6 frequency bands with operations now started. The collaboration is larger. I mean, you can think of this large aperture telescope being the equivalent of ACT, and then there are 6 more telescopes, so there are more people involved. It's a large international collaboration, hosting people from all over the world. And when the full build is finished, the plateau will host all these components. So nominal is what we proposed in 2016 as a community project to achieve our next science goals. And this comprises 1 large aperture telescopes and 3 small aperture telescopes. Then there is an additional small aperture telescope built and funded by our Japanese colleagues. 2 small aperture telescopes built in the UK, 1 in Cardiff, 1 in Manchester, that should go to site next year. And then we have received NSF funding to extend the large aperture telescope to full population of the optic tubes. And the last thing I want to mention is this array, this solar power array funded by a combination of the NSF and the UK research and infrastructure funds that will cover 70% of the operations of the observatory. So ASO is the next cosmology project. So you will get the, again, mapping of the CMB, and from that extract all the information that you want about your preferred cosmological model. But it also opens up a little bit more to all the science that we've always considered a bit of ancillary in our CMB projects, but that really happens for free in our observations. And so there is a lot to be done on galactic astronomy, time domain astrophysics, and extragalactic astronomy, because the observations are so sensitive that all of this extra science is now possible. Okay, just a couple of examples. This talk is about the small scales, so I'm not gonna cover 6 out of 7 telescopes of ESO because the small aperture telescope are purely dedicated to mapping the large scale behavior of the CMB, going after the signature of cosmic inflation. The large aperture telescope is going to provide these refined measurements of the intermediate to small scale in the CMB. We are planning to cover a wide survey covering between 40 and 70% of the sky. We still don't have a final survey strategy. With about 1.4 arc-minute resolution at 150 gigahertz and very high sensitivity. And so this is the survey mapped here that is going to give you new results on cosmological models, on the constituents on the universe, etc. Again, this is just an example of a couple of extracts from the science book. By construction, this survey has full overlap with the Rubin Observatory, and there is, of course, a large overlap with Euclid and a lot of other surveys. This is, again, enabling a huge range of cross-correlation science and combined science, where you need to pull out one lever arm from the CMB and one, for example, from the BIO or from other large-scale structure tracer to be able to break degeneracies in cosmological models. I just want to leave you with a snapshot of where we are with it. The LAT is observing. We have achieved first light in February, and I just want to show you here a comparison of what ACT has achieved in 5 years and SO in 144 hours. So it's basically already there, right? So SO is, each tube of SO is the equivalent of a full ACT for 5 years of observation. So this is gonna move the field pretty quickly and push us towards high resolution observation. And I'll just leave you with the conclusion while I play this video that show up, yeah, a combination of, well, showing how we're moving into achieving higher resolution in polarization measurements. And I think you should all watch out for high sensitivity and high resolution polarization, CMB polarization measurements in the future. Okay, that's it. I I don't have a helium fraction plot in the slides. You mean? Oh, the collection, this one. Yeah. Yeah. Yeah, we do. And well, of course, you open up along the degeneracy, and so the contours are wider. But I mean, they're low but consistent, right, with the expectation. And so then when you open them up together again, they're consistent. I might have a backup slide on that. I don't remember, but yes, we do have a run where they're both varied as well. Mm-hmm. You mean what fraction of the sensitivity to an effect it comes from the IL? Define IL for 3000. So the data set, so the ACT data set goes all the way to 6,500 in terms of CMB pure power. It's not a linear contribution, right? So you get a lot of the signal below 3000 and then you get more, but not in a cumulative, well, it's a cumulative way, but it's not linear scaling with scales. So I'm not able to tell you how much it relies on that. But we've done a lot of robustness tests on ineffective, and ineffective is basically our guinea pig. We push it through the pipeline and test everything on it because we want to check the reliability of our small scale data. So we tested by excluding temperature altogether, which is the one that has foreground contamination at high multiples. Polarization has got very little of it. Or breaking down the scales and doing less scales or reducing that. And there is a whole robustness chart in the paper that shows that the result is pretty stable. So we couldn't spot anything obvious that, you know, would indicate that it's the very high L scales that are causing that. Julian? Mm-hmm. So we had a dedicated foreground paper accompanying this release. It came out, I think, 2 months after the main set of publications where we look specifically into that. So the templates that we currently use, so the modeling that we use is not that different from previous ACT analysis from Planck, and Planck learned a lot from ACT and SPT and imported a lot from that. It's very similar to what SPT currently uses as well. And what we wanted to check is that that was the minimum model that we needed to be able to absorb all of these contributions. The issue with updating that is that the observations lag behind here, right? So you don't have accurate enough understanding of the astrophysics to be able to have better prediction in terms of the templates. But what you do have is a lot of complex simulations. And so what we did in particular is to push that model through a bunch of higher complexity simulations, so the Agora set in particular. And we found that that model was okay to perform on the simulations, but there are some components that are incredibly different across the two. And again, what we wanted to do is make sure that whatever difference was happening in the astrophysics modeling was then not going to impact the cosmological results. So we did it as a check of the model, and then we showed that it doesn't matter, or at least at the level of sensitivity that we currently had, it didn't matter. For SO, it might matter, and so that needs to be continued going ahead. I said ineffective was our guinea pig. We ran everything on ineffective because it captures, the behavior of most extensions at small scales. So yeah, we did all our tests on both. For the birefringent result, I don't have a result. That is one thing that we are eager to see revised with the first SO observations. Yeah, with the instrument knowledge that we had in hand and with the measurements that we were making, we could not confidently say that that result was a statistically significant or robust measurement of something, and so we presented it with the uncertainty associated to it that we have. Obviously, you can take it at face value and say if this is true, and then you also measure it. Like there was a recent analysis that was combining it with other observations. So if you take it at face value, then it can be, a 3 plus sigma evidence for something, but there are caveats in that number. I don't have a forecast to give you, but that's definitely something that can be revised with 1 year of observations. So it should come out pretty soon.
Okay, there are no other questions. Let's thank you immediately.